Right, okay, so today in this video we're going to be looking at the modulus and argument of a complex number. Okay, so we've seen that complex numbers are written in the form a plus bi, okay, where a and b are real numbers, and the complex number z is represented by the point AB on an Argand diagram. So remember, our Argand diagram we can sketch by having the real axis going across the way, using like an x-axis, imaginary axis is up and down, so that's the y-axis, okay, and the point z would be along A up to B, okay, so that's how we can plot A plus BI on our Gantt diagram, okay. But there's a couple of things that come from that. So the distance of z from the origin, okay, which I've noted here as r, is known as the modulus of z. Okay, in other words, it's the size of z. Okay, how big is that complex number? Okay, the angle OZ makes with the positive direction of the x-axis theta is known as the argument of z. Okay, so we can actually get the angle it makes with the x-axis, which is the real axis in this case. Okay, and that also gives us a location of where we can find the complex number. Okay, what we always do is we always choose theta such that we go between negative 180 and 180. Okay, so we never want to have an angle that goes without that region. Okay, and you're going to see why, because if our complex number does go below the real axis, okay, rather than going all the way around in a sort of anti-clockwise fashion, we can go clockwise and just take it from the negative side. Okay, so it just makes life a bit easier regarding our numbers there. Just to note also that, okay, if you've done trig, right angle trig, cos of theta would be A over R, which then if you rotated round and you simplify, A would equal R cos theta. Similarly with sine theta, you would get B equals R sine theta. Okay, so putting A and B back into what Z was originally, okay, so remember Z was A plus BI. If we change the A and the B to R cos theta and R sine theta, then what we get is Z equals R bracket cos theta plus I sine theta. Okay, and that is what's known as polar form. Okay, that's the key thing there. That's what's known as polar form. So I know I went through all that a bit quick. Feel free to pause the video and go back and read everything again and write everything down. But that is polar form, and that's what we're going to have to. That's how we can write down also, once we know what R and what theta is, how we can write down what the complex number is in polar form. Okay, and that has many advantages, which you'll see in a future video about how we can multiply, divide complex numbers with it rather than using A plus BI, which gets a bit more complicated. Also, we can find roots like this way as well. Okay, and it has a nice pattern to it as well. Okay, so we're going to look at a couple of examples, okay, in this video to show us how we can go about it. Okay, so example one. Okay, we're going to start off with a complex number, z equals 1 plus root 3i. Okay, so what we do is we will set up a set of axes. Okay, both my values are positive, so I don't need to go too far into the negatives at all here. Real goes along the x-axis, imaginary goes up and down the y-axis. Okay, so my real value, okay, the bit that's not attached to the imaginary number I, is 1, so I go along 1. Okay, so 1 would be along here, and then root 3 would be up here somewhere along the imaginary, so let's say it's there. So then that's where z would be there. Okay, so I went along 1 and up root 3 there. Okay, again, r is the length, the magnitude, the size of my complex number, and theta will be the angle that takes me from the real axis round to where my complex number is. So we're going to calculate both those things there. So using Pythagoras to work out r is going to be the square root of 1 squared plus root 3 all squared. Okay, so that gives us square root of 4. Now, because it's a size, we're not going to take the negative value of this. Okay, we're going to take the positive value, which is 2. Okay, square root of 4 will take us 2. So that's the size there. Using trigonometry, okay, now I know we've worked out the size of r as 2, but we're just going to use our base values of 1 and root 3 to get theta here. So if we use tan, so tan theta, because it's opposite and adjacent, tan theta would be root 3 over 1, which again just simplifies to root 3. And again, using your exact value triangles from last year, at higher, theta then becomes the tan inverse of root 3 over 1, and that would be theta is 60 degrees, which is, in radians, pi over 3. Okay, so that's what theta is there. So writing this in polar form, we know z is r bracket cos theta. Oh, let's try that again. Cos theta plus I sin theta. So putting in our values, r was 2, so we've got then cos pi over 3 plus I sin of pi over 3. Okay, and that's how we've got our values there. Okay, we're okay with that first example? Alright, so that's just a nice one because the values are positive, we don't have to think too much about the angles and that, but that is the setup we're going to do for all the questions, okay? We'll now look at another example now, okay? So example 2, okay? We're going to let z equal -1 plus I. Okay, so -1 plus I. So this time round, we can see we're going to have to go along the negative side of the real axis. So I need to go along to -1, and I need to go up 1 in the imaginary, so my complex number will be there. Okay, that's where z is going to be there. Okay, now I'm going to draw the triangle this side here, okay, because I know that's me along from the origin, okay, along 1 unit to the left and up 1 unit, okay, in the imaginary axis, and r is going to be there, okay. So remember what theta is. Theta is the angle it makes with the real axis, but from the positive part of the real axis. So theta is actually going to be here, okay. How we're actually going to work theta out in this case is we're going to have to work out what this angle is in here and take it off 180. Okay, so let's call this angle alpha. Okay, so we'll work out alpha using our triangle, and then we can use that to help us work out what theta is for the one we need for our complex number. Okay, so that's going to be the setup in this case. Again, r, using Pythagoras, is my length, so I had to go along 1 and up 1. So it'll be 1 squared plus 1 squared and the square root. That would eventually lead you to the square root of 2. Okay, for that one there. Now, we're going to work out alpha using this. So alpha is going to be over here, and then that's going to be opposite over adjacent, so it's 1 over 1, which just becomes 1, okay? So then alpha will be the tan inverse of 1. Okay. And using your exact value triangles from last year, okay, you would have got that alpha is 45 degrees, which is pi over 4. Okay. However, that's alpha, we want theta. So then theta is going to be pi, which is 180, minus pi over 4. Which leads you to 3 pi over 4. Okay, which is 135 degrees. Okay, are we okay with that step there, yeah? That extra step. Do you understand why we've got to take that from 180, yeah? Yep. Okay, perfect. Alright. So, putting that again into polar form, we can now do that now. So our complex number z was r cos theta plus I sin theta. So that's going to be square root of 2, because that's what r is, cos 3 pi over 4 plus I sin 3 pi over 4. Okay, so that's the second example. You can see there was a little bit extra work just because of what quadrant we were sort of in the coordinate scheme. Okay, in our Argand diagram. Are we okay with that? Any questions on that one there? No? See, it's fairly similar to the first one though, yeah, just that extra step. Right. Perfect. Okay. Right. Look at a few others. Again, we're going to look at what happens in the other quadrants now as well. Okay, just so you've got an example of all. So, another two examples. Example 3. Okay, we're going to let z equal 2 root 3 minus 2i. Okay. So you can see here that I'm going to have to go along the positive side of the real axis, okay, because I'm positive 2 root 3, but I'm negative 2i, so I'm going down the imaginary axis here, okay, so imaginary axis over there, real axis along here. So I'm going along a value 2 root 3, so it'll be over here somewhere, and then I'm going down to negative 2 on the imaginary axis, so that's where my z is going to be there. Okay, so why we take theta to be between negative 180 and 180 is for this reason here. Okay, so rather than normally taking it from, we've got to take it always from the positive real axis, but rather than going all the way around to describe it, we can just go the opposite way. We can go in the clockwise fashion. So that's what theta is going to be here. Okay, we can do that because it'll be less than 180 around the negative. Okay, it's going to be a negative one, but that's what's going to be there. Okay, so again, from a triangle 1, so to work out r, so I know that is a length of 2 there, I know that's a length of 2 root 3 I went along there. Okay, so let's work out these from here. So r is going to be, in this case, the square root of 2 root 3 all squared plus 2 squared. Okay, so if you square 2 you get 4, if you square root 3 you get 3, 4 times 3 is 12. 2 squared is 4. That becomes root 16. Again, we'll take the positive one only. R has a length of 4. Okay, so the modulus is 4. Theta, so again, it's tan theta, opposite over adjacent, so it'll be 2 over 2 root 3. The 2's cancel, so you get 1 over root 3 like that. And again, that's one you can get from your exact value triangle. Okay, so theta would be the tan inverse of 1 over root 3. Okay, now I forgot to actually show you what your triangles look like. So remember, how you remember it is that sine 30 is 1 over 2. So therefore root 3 is down here. Therefore you get pi over 6, which is 30, pi over 3 in there. So if I'm wanting theta to be the tan inverse of 1 over root 3, therefore it's opposite over root 3, so that means it was the pi over 6 angle I was using there. Okay, so theta is 30 degrees, but also pi over 6. Okay, that's how the other ones worked as well, plus you had the other one for the 45 degree one. Okay, so that is the correct angle we need. We just need to remember though that it's negative, okay, because we went down this way, haven't we? We've not went across like the normal way, we went down this way. So in this case here, okay, therefore theta is actually negative 30 degrees or negative pi over 6. Okay, so that's what we're going to have to put into our function, our complex number there. So z being r cos theta plus I sin theta. So it's going to be r is 4, then cos of negative pi over 6 plus I sin negative pi over 6. Okay, and you can actually physically see how that's easier to plot than what that would be if you took it all the way around from the positive real axis, okay, which would then give you 7 pi over 6, 11 pi over 6 I think it would give you, or something like that. So, you can actually just physically see it's easier just to go around that way. Okay, so that's the first example you've seen where the actual argument has been on the negative side of the Argand diagram. Are we okay with that? Any questions on that one there? No? Right, okay, just one last one then. We've got one lost quadrant we better show you an example of, and that'll be us for today. So example 4, So I'm going to let z, where both ones are going to be negative, so it's going to be negative root 3 minus 3i. Okay. So if we have our two axes shown here, real and imaginary. So it's telling me to go along to negative root 3. Negative root 3 be along here. And then down 3. So my complex number would be there. Okay. So again, we want theta, which is going to be there. Okay. But we're not going to be able to work that out from a triangle. So again, we're going to call alpha into there. Alright, so that's how we're going to do it. A bit like the second example we've seen there. So we get our lengths from our triangle, okay, so we had to go along root 3 and we had to go down 3, and that's going to be our lengths there to help us work out r and theta. We're okay with that diagram? Yep. Okay. So, yeah, we've seen this now. Square both lengths, okay, so it's going to be root 3 all squared plus 3 squared. So that's going to give me 3 plus 9. It's going to be the square root of 12. Okay, which again you can simplify down in thirds to root 4 times root 3, which gives you 2 root 3. Okay, so always simplify down your thirds if you can. Okay, right, we're going to have to work out alpha to help us work out what theta is. So alpha is going to be, tan of alpha is going to have to be opposite over adjacent, so it's going to be 3 over root 3. Okay. Now, if you remember this thing from National 5, obviously you've probably done a lot of it at higher last year, you can, in order to work out what this really is, because it does simplify down, you times, you rationalise the denominator. Do you remember that? Yep. So if you times both by root 3, you get 3 root 3. Root 3 times root 3 is just 3. The 3's cancel, so you get root 3 over 1, which is just root 3. Okay, so tan of alpha, we will work out to root 3, so then alpha is going to be the tan inverse of root 3. So again, if I go back up to the triangle that I had in my last example here, so tan is always opposite over adjacent, which means to get root 3 over 1, I need to use pi over 3, which is 60. So then alpha is going to be 60 degrees, or pi over 3. Okay, again, we'll use the radians there as well. Okay, now we know this is negative, right? Because it's on the other side of the bar. Don't treat it like a negative, the final answer, okay? Because we still want to work out what theta is here. So we need to know what this angle theta is. So theta is going to be pi take away pi over 3. Okay, which gives you 2 pi over 3. So what that really means is the theta is negative 2 pi over 3. Okay, because it's on the underside of the real axis there. Okay, so z r cos theta plus I sin theta. So that's going to equal r is 2 root 3 cos of negative 2 pi over 3 plus I sin negative 2 pi over 3. Okay, so we've achieved to write that in polar form. Okay, that's going to be the last example of the video. Is there any questions?